Hello learners, BME 025 Condition Monitoring and Maintenance Management. Video 15 Maintenance Models 1 presented by myself Dr. N. Venkateshwarlu, Professor, School of Engineering and Technology, IGNOU, New Delhi. Introduction. We all agree that the failure frequency can be reduced by employing suitable and timely actions. This is possible if the area that is causing more loss or disturbances to the production is identified. At the same time, one should remember that it should be cost effective. Therefore, it must first be decided whether it is worthwhile to study. After identifying the area of study, it is important to lay down a path, method of study and analysis. The next objective is to fit a theoretical distribution to a random sample of failure or repair data, that is, to perform a statistical test in order to accept or reject the hypothesis that the observed times comes from a specified distribution. Now we discuss the procedure for identifying and specifying candidates distribution for fitting the data. In this video, we will learn the procedure to reliability models and a few goodness of fit tests available for conducting the testing of hypothesis. The particular probability distribution addressed includes the exponential, variable and normal and log normal distributions. Objectives. After listening to this video lecture, you will be able to identify, collect relevant data and analyze a problem related to reliability of the equipment, conduct trend analysis and examine various reliability centered maintenance models for fitting the data. Conduct a goodness of fit test and confirm the distribution of failure patterns. These are the various objectives we are going to learn in this video. Identification of the problem and data collection. So first of all, one has to identify a problem. How to identify the problem? Once identifying the problem, one has to collect the data. So in this, appropriate data collection after identifying the problem is one of the most important steps in reliability analysis. A data collection must be designed, developed and maintained to facilitate correct and effective reliability analysis. The use of the collected data may be one or more of the following. Detection of in-service problems leading to production losses. Evaluation of reliability and maintainability characteristics. C. Studying the economics of system breakdowns. D. Feedback to manufacturer for design modification if needed. Data on reliability characteristics can be obtained by two methods, either directly from the field or from the sample testing in laboratories. For an effective reliability program, the collection and analysis of the failure statistics such as failure modes, their frequencies and possible causes of failures for each component and equipment type from a representative population operating under identical condition is needed. Data collection in field is an expensive and time consuming work. Nevertheless, data acquired from field is the best representative of the system reliability and maintainability characteristics, and all efforts should be made to collect data from the field. Some of the points which are of practical importance for development of field data collection systems are given here. Mahan 1972 or Arison 1988. A. The depth of reporting and data collection should vary according to the importance of the equipment or its components. Reporting should be confined to facts, opinions in the engineering judgment category should also be included. C. Attempt should be made to collect only those data that are likely to be useful. Procedure for reliability centered maintenance modeling and analysis. After distinguishing between the repairable and non-repairable items, the reliability study can be established as it suits to the requirements. The most useful and universal procedure of reliability centered maintenance modeling for repairable equipment is narrated here. The field data is collected for the equipment categorized under repaired items in the form of time between failures and time to repair. The data inconsistencies and errors are removed and the refined data is analyzed by both the types of models, example graphical and analytical models. However, more important is given to graphical methods since they can give more and simple understanding and can be easily reproduced. The graphical tests such as eyeball analysis, cumulative plot test and serial correlation determines the presence of trend. The machines which exhibit presence of strong trend are further analyzed and fitted into non-homogeneous Poisson process model. Power law process model, one of the most popular and commonly used NHPP models, can be used for such study. If there is no trend, it confirms the independently and identically distributed assumptions. The values obtained can be checked with some analytical tests such as Laplace test. The machine free from trend are further graphically analyzed through total time on test TTT plots. The exponential fit that confirms homogeneous Poisson process HPP models can be known from the analysis. Otherwise can be categorized as renewable process model, which is in accordance with the Weibull pattern. The goodness of fit analytical tests can confirm this, otherwise can identify the actual distribution from which the data has come. Thus, reliability characteristics and maintenance schedules can be estimated. Further, their reliability growth plots can also be drawn to estimate the improvements. Algorithmically, it is explained as given below and followed by a flowchart in figure 8.1 in the unit 8. Algorithm. Step 1. Identification and definition of problem or setting the hypothesis. Usually, the reliability studies consumes much cost on time. In addition, it requires higher level engineering knowledge to understand the complex problems and models. Therefore, it should be first decided whether the study is worthwhile or not. Hence, it is often suggested to select the area where the cost of breakdown is very high or any failure is hazardous or leads to catastrophes that may claim human lives. Assets and or environmental disorders. Once the decision is taken, problem should be defined clearly and the bounds of the study is also be demarcated. Otherwise, it becomes endless project. However, improvements can always be incorporated at the later stages based on the feedback reports. A suitable hypothesis stated for the equipment upon which the reliability studies are to be conducted. Step 2. Collection of relevant data. So, relevant data is collected often in the form of time between failures, in short called TPF, and time to repair, concisely called TTR in the case of repairable items, or time to fail in short called TTF in case of non-repairable items. See figure 2. While collecting such fields data, there may exist some practical problems. Suitable assumptions as applicable may be made to overcome such problems. The data so collected is to be tabulated. Step 3. Elution of data inconsistencies and errors. To err is human. There is very possibility of occurrence of errors in the collected data. Such suspicious entries may be eluded. Further, in some situations, there may be some inconsistencies in the data of TBF values. For instance, a particular machine, say an automobile, may be under breakdown, non-available for the want of some spare parts, say a valve for a tire. If there is any delay in supply of such spare part, the machine can be restored to up condition and the downtime will increase. Suppose this continues for a very long period, the machine should be deleted from the list completely. Similar inconsistencies, if found, should be precluded for the analysis. Step 4. Trend analysis and correlation test. The trend analysis gives us the idea about whether the machine is deteriorating or improving, by which we can also understand which phase of life cycle bathtub curves the equipment is experiencing, infancy or youth, old age, various graphical eyeball analysis, cumulative plot test, etc. and analytical methods, Laplace test and Mill HDBK 189 test are available for testing the trend. The correlation and regression analysis also can aid the study in confirming the time independence of the distribution. If the trend is positive, assumption of independently and identically distribution is said to be not contradicted. Hence, we can fit the data in non-homogeneous Poisson process NHPP models such as power law process PLP. So, in contrary, if the data does not exhibit any trend or very weak trend which is not considerable, then we have to go for further analysis by total time on test, plotting or other suitable reliability models. Then step 5, TTT plots to examine exponential fit total time on test graphs can be plotted in several ways. The most popular and convenient methods are maximum likelihood estimation, piecewise exponential estimation and product limit estimation or Kaplan-Meier estimation. With the help of TTT plots, we will be able to know whether the data has any exponential fit. If there is exponential fit, we can model the data in homogeneous Poisson process. Otherwise, it can be fit in renewable process such as Weibull model. Step 6. Fitting the suitable model. Using relevant statistical tools, the data is fit in suitable models. Its characteristics can be hence studied to design the reliability of the system. Step 7. Confirmation tests and goodness of fit. Further, the fit of the model can be confirmed by various statistical methods or hypothesis tests. The general goodness of fit tests such as chi-square tests are universally applicable, while some specific tests are available to check particular distributions. The specific goodness of fit tests such as Bartlett's test, exponential distribution, Mann's test for Weibull distribution and Kolmogorov-Smirnov test for normal and log normal distributions are the few found among most useful tools in this study. The goodness of test not only confirms the distribution but can authenticate the methodology or reliability analysis. Step 8. Reliability centered maintenance planning and scheduling. The reliability characteristics are then estimated. Various characteristics such as T optimal, T median, T mode, B1 life and B.1 life, etc. can be estimated, and hence maintenance planning and scheduling can be done. Step 9. Reliability growth testing. Further, the reliability growth can be tested using suitable growth models such as Dawn's growth model, AMSA model in test fix cycle. So, statistical preliminaries in reliability evaluation. Probabilistic nature of system reliability arises from the fact that the performance parameters, which is random variable of the system, follows a pattern which may be expressed in probabilistic terms. The function which describes this pattern or distribution of the performance parameters of a system is known as the distribution function. If the particular set of performance or failure are well represented by a particular distribution, it can be concluded that the failure characteristics follow that particular distribution. A brief description of the basic fundamental theory is presented in the section to follow. Probability functions. The probability and availability studies involve use of mathematical and statistical models which are probabilistic in nature. The probability function important for the development of reliability, availability and theory are: A. Probability density function PDF, cumulative distribution function CDF, reliability function R, RF or hazard function H. So these are the four methods of reliability and availability theory. Probability density function. The probability density function is the basis for predicting the behavior of any probabilistic situation such as reliability of or availability. Given the PDF, one can compute reliability function and instantaneous density function FT, usually referred to as failure density function. Cumulative distribution function. This function defines the probability that a random variable T lies between some lower limits, often 0 and upper limit T, for a continuous variable such as time to failure. The cumulative probability Ft is given by the integration of density function between the limits required, that is equal to Ft is equal to integral fx dx. Reliability function. The reliability function RT, which is defined as the probability of a system or an item to perform or operate its required function without failure under given conditions for an intended period of operation, and it is mathematically given as RT is equal to 1 minus Ft, that is equal to 1 minus integral fx dx, that is equal to integral R dx. This is reliability function. Hazard function. The hazard function T or instantaneous failure rate function is a conditional expression that an item in service for time t will be in the next instant of time dt, given that it has not previously failed, survived up to time t, that is p, the unit will fail in t, t t dt, that is equal to lambda t dt. So where lambda t is the hazard rate at time t and p is the probability of occurrence, the mathematical relationship between failure density function ft and hazard rate lambda t is, that is equal to lambda t is equal to ft divided by 1 minus ft. The general equation showing the relationship between the reliability function rt and hazard rate, that is equal to rt is equal to exponential in bracket minus integral lambda x dx. When lambda is the independent of time, as in the case of constant failure rate, expression reduces to rt is equal to e to the power of minus lambda t. Then trend test. By checking the trend, we will be able to understand if the machine is improving or deteriorating, that is DFR or IFR. The TBF of the equipment, time between failures of the equipment in chronological order, can be analyzed for the presence of trend to know whether the equipment or the item is deteriorating or improving with age. So with trend test we can find out the life period of a machine. Is it deteriorating or with the age, or it is it's not showing it is good, or it is improving? That we can find out with the trend test. By simply plotting cumulative TBFs against the cumulative number of failures, we can test whether the machine or item under consideration is improving or deteriorating. If we get a curve concave upward, this means that the TBFs are becoming shorter and shorter, that is to say the machine is deteriorating. On contrary, if we obtain a curve concave downwards, this means that the machine is improving. So with this, the trend test we can find out the by plotting a by conducting a trend test we can find out the machine's health condition. If the data exhibits linearity, the plot is said to have no trend, and the failure data is known as independently and identically distributed and can be further analyzed by statistical distributions. The trend test eyeball analysis. So in this we pass our eyes through chronological times between failures and search for the increase or decrease of the failure rate. That is, if the TBFs are showing increasing in magnitude towards the end, it shows decreasing failure rate. If the magnitude of TBF is approximately constant throughout the period, then it shows constant rate of failure. If there are an increasing number of failures for each period, then it indicates increasing failure rate, and so on. Conclusions. Learners, I hope you understand the following: identification of the mission problems, then data collection procedure for reliability modeling and analyzing the data, and the trend test conduction for knowing about the machine condition according to the age of the machine. So this is the various objectives you have learned in this video. So with this, thank you.